Oscilloscopes have always been the tool of choice for engineers debugging electronic devices. The most critical parameters for verifying digital designs are time-related. Rise and fall times are of fundamental importance. Clock and data timing and phase relationships need to be precisely controlled. The new generation of mixed signal designs employ digital control techniques, but are also processing a broader range of analog signals, including sensors, smart power controls, and more. In addition to timing parameters, we need to observe and measure characteristics such as total harmonic distortion, crosstalk, and noise. A conventional oscilloscope with 8 bits vertical resolution delivers 256 levels, which is fine for timing measurements, but for mixed signal designs the required oscilloscope specifications are more challenging. Designers need to make measurements with higher resolution and improved dynamic range. The Picoscope 5000 series is the first flexible resolution oscilloscope that can make 8, 12, 14, 15 or 16-bit resolution measurements. Changing from one resolution to another is a simple front panel control that can be selected by the user. Internally, multiple high-resolution analog to digital converters are employed in different time-interleaved and parallel combinations to deliver either high sampling rate of a gigasample per second or high resolution of 16 bits, and other combinations in between. But improved resolution is of little benefit unless accompanied by improved front-end performance. The Picoscope 5000 is specified with greater than 70 dB spurious-free dynamic range. Next, we'll have a look at a demonstration of the Picoscope 5000. This demonstration will show how the scope can switch from 8 to 12 bits resolution to reveal characteristics of high-frequency noise that are interfering with a low-frequency signal. In this demonstration, I'm using a Picoscope 5444B flexible resolution oscilloscope to look at the characteristics of a low-frequency sine wave. I have the instrument set up with a time base of 20 microseconds per division, 50 megasamples of buffer memory, 8 bits resolution. First measurements that I can make are with the rulers here, so I've got the period of the waveform is about 50 microseconds, which means we're looking at a frequency of 20 kilohertz. I can use the horizontal rulers to look at the amplitude, so the peak-to-peak amplitude of the waveform is about 1.85 volts. There's also a range of automated measurements that I could apply to the waveform down here. But looking at that waveform, I can tell that it's not perfect. There is some noise that is affecting the characteristics of that waveform, and I'd like to investigate that noise in a bit more detail. Most oscilloscopes have an average function, which delivers a mathematically averaged trace of the acquired waveform. So we can do that and see if it helps us to characterize the noise that we're seeing on this sine wave. So if we go to math channels, average, that's going to give us by default an average of the last 16 acquired waveforms. Turn that on and we can see the average waveform there, the one in the black trace there. If I just freeze that for a moment and look in a little more detail at what it's captured with the zoom button here. Well, we can see again the blue channel is the zoomed in version of the 8-bit acquired waveform, and the black channel is the average waveform. It's certainly cleaned up the information that we captured previously, and we can see a few little peaks and troughs in there, but it's not really giving us any useful information about the noise that is sitting on the top of the low frequency sine wave. So we need to find another technique. Some oscilloscopes offer a high resolution mode which uses a boxcar moving average to generate an improved resolution image of the waveform. And we have that on the Picoscope too. So if I go into the channel menu here, and we call it resolution enhancement, and we can choose the number of bits of resolution enhancement that we want to achieve. So we'll go all the way up to 12 bits enhanced resolution here and see what it does for us. So we've acquired the waveform. We'll zoom in again, and again we're seeing some interesting information, but the shape of the noise that is sitting on the top of the sine wave, it looks a little strange. It looks odd and difficult to analyze at this point. So it still hasn't really given us the information that we need to draw any firm conclusions about the characteristics of that noise, and from there what we might do about it. A unique feature of the Picoscope 5000 is its ability to switch from 8 to higher bits of resolution. So in hardware it can switch from 8 to 12, 14, 15 or 16 bits of resolution. So what I'll do for looking at this waveform is to switch to 12 bits of resolution. You might just hear a click from the scope as I make that transition. Now we're acquiring the exact same waveform but with more bits of resolution. So if I freeze the acquisition, then use the zoom tool to look in more detail at what's going on, now we can see with complete clarity what the characteristics are of the noise that's sitting on top of that waveform. And I can use the rulers to make some measurements on that. So let's have a look at make a measurement of the period. So the period is about 1.1 microseconds. So the noise that is interfering with the waveform, with the sine wave, is a little under 1 megahertz in frequency. In amplitude we're looking at about, let's see here, about 37 millivolts. But probably even more important than that, we can look at the characteristics of it. We can see that it is a triangular waveform that is noise that's sitting on top of that sine wave. So that gives us the information that we need to go and search for the source of the noise that is causing the problems to the acquired waveform that we saw in the first place. We're now seeing it with good clarity, enough to make measurements and draw conclusions which will help us to find the root cause of the problem.
In summary, we've seen that the Picoscope 5000 series has a novel architecture in which multiple high-resolution analog-to-digital converters are used in different combinations to boost either the sampling rate or the resolution. The oscilloscope can sample at 1 gigasample per second with 8 bits resolution, or 500 megasamples per second at 12 bits. It can be increased to 14 bits at 125 megasamples per second per channel, revealing every detail of a signal in a crystal clear display and better than 70 dB spurious-free dynamic range. If only 2 channels are required, then resolution can be increased to 15 bits, and in single channel mode all the analog to digital converters are combined to give a 16-bit mode at 62.5 megasamples per second. For more information on Picoscope flexible resolution oscilloscopes, please visit our website